This is a question I gave in class with a video. It's got a video. So, and it was based on, the Super Bowl. So the question is, what angle should you throw a football so that it goes the maximum range? And I gave multiple answers, and I love this question because there's no necessarily correct answer. Like I said, I did record this video for a different project. If you know what that project is, I'm impressed. So 45-degree angle, greater than 45-degree angle, less than 45-degree angle. It depends on the speed. It depends on other stuff. Generic. So I think you could argue. That any of these would be the correct answer or the best answer. So I'm going to do this problem. I'm going to do it on paper, and then I'm going to do it in Python, and then I'm going to do it in Python again, and it's going to be a whole bunch of great stuff, and I'm excited. So let's get started. Jumping over here, back to the paper. Let's do it. Okay, switching to paper. So imagine that we have the following situation. A ball is launched. And I'm going to do this projectile motion a little bit differently than some other places may do it. I'm going to try to use proper vector notation for the most part, and I'm going to use the momentum principle. So let's start with the momentum principle. This says that the net force acting on an object is equal to the change in momentum with respect to time, and momentum is mass times velocity, so I can write this as mass times the change in velocity with respect to time. Force is a vector, velocity is a vector. Mass is not a vector, it's a scalar. And once I throw the ball, because that's not me throwing the ball, I don't know if you know that, in that video, that was not me. I'm not that tall or able to throw. Once it leaves the hand, let's assume for now that the only force acting on it is the downward gravitational force, Fg. So the gravitational force is mass times this vector 0, negative 9.8. 0, we often call 9.8 g. So this is 0, negative g sometimes. In terms of the initial velocity, we can write that. I want to find the angle that I throw that at. So if I throw this at some angle with a magnitude v0 at an angle theta, I can find the x component, vx, and the y component, vy, that's a theta, with this right triangle right here. So if I take the cosine of the angle, I get adjacent over hypotenuse. So that gives me the I'll call it v1x. The x component of the initial velocity is v0 times the cosine of the angle theta, and then v1y, the y component, I deal with the sine, so that's going to be v0 sine theta. So that's how I get this up here. Okay, so one other thing. I know something about the initial position and something about the final position. I know the initial position vector. I'm going to set that equal to 0, 0, 0. It doesn't really matter, but I'm going to do it anyway. You can put the origin anywhere you want. And if that's the case, it's going to end up with a y value of 0 because it's going to get back to the ground. And I want to find the final x position. So that's my goal here, is to find that final x position. Let's start off with something as a vector. I'm going to write the following. Average velocity is the change in vector position over the change in time. That is true. This is how we define average velocity. Now, in the rate of change of position as a vector, vector. Now, I can also write this as v1, the initial velocity vector, plus v2, the final velocity vector, over 2, the average. I can do this if the force is constant. If the force is not constant, then you can only do that if delta t is very small. Okay. So, but in this case, I have a constant force, so I can say the average force is this. Now I have an expression right here for delta r that I want to find the final r. So let's just solve this for delta r. I'm going to multiply both sides by delta t, so I get delta r. It's going to be v1 plus v2 over 2 over 2, all of that times delta t. All right, I split that up. Now, let's go ahead and break this into an x and a y equation. Because if I look right here the change in momentum depends on the force. And in the x direction, the force is 0. So that means the change in momentum and the change in velocity have to also be 0. So I'm going to break this into, I'm going to write this as an x equation. I can't spell it. Equation. That's terrible. And a y equation. I did a equation. I'm thinking about x's and y's. So in the x equation, I'm going to say delta x is going to be equal to v1x plus v2x, all of that over 2 times delta t. And I know I said I wasn't going to do that, but I just did. And in this case, since the force in the x direction is 0, the change in momentum in the x direction is 0, so the initial velocity and the final velocity are the same. So if these are the same, I can write this as v1x delta t, because I have 2 of them, I divide by 2, and that's that. So that's really what I want, right? I want to find the change in x. I'm just going to leave it like this, delta x. Actually, that's delta t. Let me write it as delta x is v0 cosine theta delta t, because that's my initial x velocity. Now I need to find the time. That's my problem. I need to find the time. Well, let's look at this same equation in the y direction. So I'm going to say v average y is going to be equal to v1y plus v2y over 2. That's the average. It's also going to be equal to delta y over delta t. I want to solve for delta t, right? So let's multiply both sides by delta t. Again, I get delta y. It's going to be v1y, sorry about that, plus v2y over 2 delta t. No, 2 times delta t. But I don't know delta t. Okay, now we can use the momentum principle. The momentum principle in the y direction said F net y is negative mg, and that's going to be equal to m delta vy over delta t. I know this, right? That's from the force in the y direction. The mass cancels, so that's good. And now I can write this as v2y minus v1y over delta t. It's the final velocity minus initial velocity divided by the time. Now I'm going to multiply both sides by delta t. I get v2y minus v1y equals negative g delta t. And I'm going to add this to both sides. So I get v2y, the final y velocity, is the initial y velocity minus g times delta t. I'm sorry, I didn't want to do that. No, I do want to do that. Now, I'm going to put this in right here. Instead of v2y, I'm going to put this in. So I'm going to divide both sides by 2. So I get, and multiply everything out. v1y over 2 delta t plus v2y over 2 delta t. But here I have this. So I get plus v1y delta t over 2. That delta t came from right there. And then I have this term divided by 2 times delta t minus 1/2 g delta t times delta t. So I get that delta t squared. And that's delta y. Now you'll notice these two terms are the same. So I get delta y is v1y delta t minus 1/2 g delta t squared. And now I'm going to put in my expression for v1y. So this is going to be v0 sine theta delta t minus 1/2 g delta t squared. And that is one of the kinematic equations. I derived it without calculus because why the heck not? Going back to our problem, we do know something about delta y. I know that delta y is 0, right? Because it starts at the ground, it ends at the ground, that's 0. So I get 0 equals v0 sine theta delta t minus 1/2 g delta t squared. I'm going to add this term to both sides. I get 1/2 g delta t squared equals v0 sine theta delta t. I'm trying to get delta t, right? Because remember, I need that for my x equation. So I can divide both sides by delta t, and then I can divide both sides by g and multiply by 2. I get delta t equals t V0 sine theta, there's a 2 there, over g. Let's just check the units here. V0 has units of meters per second. G has equivalent units of meters per second squared. So the meters cancel, and this one of the seconds cancel, and I get seconds. Sine theta doesn't have units. It's a ratio. And whenever I say ratio, I think of that. I'm not even going to say it. Andy Griffith show, and he said 1.5 kids are poor in the county, and Opie says, how do you have 1.5? How do you have half a kid? He says, it's not a half of a kid, Opie. It's a ratio. And then Opie says, poor Horatio. I just love that. Okay. So here's my x. I'm going to put in my expression for delta t. So let's start a new sheet of paper. So write down these two expressions. I have delta t is 2 v0 sine theta over g. And then I had delta x is v0 cosine theta delta t. So if I put this in right there, I get delta x, which is what I'm looking for. How far did it go? Equals v0 cosine theta times 2 v0 sine theta over g. And let's simplify that as 2 v0 squared, dunk, dunk, times cosine theta times sine theta, all of that over g. And again, this is going to be meters squared per second squared divided by meters per second squared, so I get meters. That's good. And this is a dangerous equation, but it's important. A lot of times you'll look this up as the range equation. I'm going to put EQ in because I made such a mistake last time. And it tells me if I know my initial velocity and my angle, I can find out where it lands. If, this is a big if. That's not very big. This is a big if delta y is 0 meters. We assumed that, right? And that's important. If that's not true, then this doesn't work. And that's where people get in trouble. But anyway, let's see if I want to increase x the most. Well, of course, if I increase the velocity, I'm going to get a greater range. But what if I want to just throw it, I want the angle? Well, remember, cosine of theta is between -1 and 1. But if I have an angle between 0 and pi over 2, so 0 to 90 degrees, then cosine of theta is going to go from 0 to 1. Sine theta is going to go from 0 to 1. It's going to have that range. So when is cosine theta 0? Well, that's true when, let's say, when it's pi over 2, 90 degrees. This is 1 when it's pi over 2. So as you go from 0 to 1, cosine goes from 1 to 0. When you go from 0 to pi over 2, this goes from 1 to 0. As you go from 0 to pi over 2, this goes from 0 to 1. So if you think, as these both change, there's one point right in the middle where they're both kind of the same. And you can make a graph of this, but if you plotted this, here's cosine as a function of theta. It goes like this. Here's sine as a function of theta. It goes like this. Oh, does it? No, it goes like this. Yeah. And so right here where they're at the middle point is pi over 4. Now, you don't have to believe me. You can try it. Okay. So that which is theta equals 45 degrees. And there's a trig identity you can do, but I hate it. I always forget it. So let's just try this. I'm in degrees mode. So let's just try multiplying sine times cosine. Let's try 40, 45, and 50. I'm just going to do those. So let's do 45. So I'm going to do cosine 45 times sine 45 equals. And I get 0.5. Now, what? I did 45. Let's see. Cosine 40 times sine 40 equals 0.49. And I just did the 45s. I got 0.5. And then if I do 50, sine 50 times cosine 50, I get that same value. Okay, so they're both lower than 45. So you can play around with that all you want, but the answer is 45 degrees. So is the maximum range 45? It could be. if, and it's a big if right there, if it's level ground and the gravitational force is the only force. But a football, if you throw it really far, it does have another force acting on it. So let's imagine that I throw a football. That looks pretty good. So it's moving this way with some velocity, v. And there's the gravitational force pulling down on it, mg. There is another force. I mean, if you take a ping pong ball like this and throw it, it's not gonna do what you'd expect. And I colored half of it because it's a moon. Okay. There is a backwards pushing drag force, and we can model this drag force as the following. We can draw it like this. I'll call it FD for drag, and I'm going to say FD is -1/2 rho A C magnitude of V squared V hat. And that's the drag force. So in this expression, rho is 1.2 kilograms per cubic meter. That's the density of the air. A, I should have drawn this backwards. A is the cross-sectional area. So a football has a cross-sectional area of a circle. If you look at it, it looks like a circle headed on. And this assumes that you throw it the way you would best throw it. C is a drag coefficient. It's a property that tells you how essentially aerodynamic it is. For a football, C is approximately equal to 0.5, although it depends on the spin, it depends on how fast you're going. That's just an approximation. We're going to use that anyway. And then V is the magnitude of the velocity, square it. V hat is a unit vector in that direction. Negative V hat tells me that the drag force is in the opposite direction. Now, but we have a problem here. Because if I want to do the same problem with this drag force, I'm in big trouble. I'm in big trouble. Because as this ball moves, the velocity changes direction, the velocity changes magnitude. So the force is not constant. So that whole thing about what is the average velocity is no longer true. I can't even find the net force, right? Because the net force is not constant. So I'm in trouble. But I can write the expression for the net force. I can say F net is equal to mg minus 1/2 rho A C magnitude of the velocity squared V hat. I can calculate everything here, and I can set that equal to the change in momentum with respect to time. If, now you should know where this is going, if I break this into small time step, delta t is 0.01 seconds, let's say, then I can assume this doesn't change that much over 1/100th of a second. And if that's the case, I could say this is P2 minus P1, the momentum at the end of the time interval minus the momentum at the beginning, and I can use that to solve for the momentum. I can say the momentum at the end, P2, is P1 plus F net, which I just calculated, delta t. And then I can use this momentum to find the new position. R2 equals R1 plus P2 over M delta t. That's the average velocity. It's not, but it's close enough. And then I can update the time. T2 is T1 plus delta t, and then I can go back up here. Now I know a new velocity. I have a new force. So I need to redo this. And that's what we're going to do. And so if it's in the air for 1 second, I would need to do 100 of these loops, which I don't want to do. Okay, so we're going to do it in Python. Yes, Python. I'm not going to model it visually. I'm just going to calculate it, and then we can plot it. Okay, so here's the football throw. We're done with that. I'm going to close it unless you want to look at one more time. Too late. Okay, so I'm just going to enter some parameters here, some constants that we're going to need. Let's start off with G equals vector 0, negative 9.80. The mass of the ball, I looked that up. I wrote it down, 0.42 kilograms. I'm not going to put my units or anything like that because I got a lot to do. And then I have the drag coefficient. I said 0.5. Up here I have 0.05. I'm sorry. So that's C is 0.05. And I don't even know if that's correct or not. Well, let's go with it. That seems kind of small. I'm kind of questioning my choices now. Let's just switch to this and Google it. Drag coefficient for a football. Let's see if we get that. 0.18 to 0.2. Okay. Let's go with 0.18. I don't know where I got 0.05. 0.18. Rho is 1.2. That's the density of air. The radius of the ball I did calculate as 0.084 meters. So area is going to be pi times r squared. Okay, now I need initial position. I'm just going to call that r, and it's going to be at 0. I need initial velocity. V0 is 20 meters per second. That's a fairly average football throw, and that's fine. And then I need an angle theta. Let's throw it at 45 degrees. I'm going to convert that to radians. Now I can calculate the initial momentum. So I'm going to say P equals m times V0 times vector cosine theta sine theta 0. So I've done everything as a vector, right? Because it's going to make my life a lot easier to deal with these things as vectors. Now I need t equals 0, dt equals 0.01. Now we're ready to do the loop. So let's say while, I'm just going to start off an easy way. While t is less than 1, I'm not going to put a rate statement in there because I don't care how fast this thing goes. Just go as fast as you want. And that's fine with me. So the first thing I want to do is to calculate the net force. So let's just write that as F net is equal to m times g minus 0.5 times rho times a times c times v squared. So v squared is the magnitude of the velocity. Now, let's go up here and say v equals p over m. I like to deal with momentum, but I'm just going to go ahead and calculate the velocity and then use it down here. So this is going to be magnitude of v squared. And then I need to multiply that by the norm of v. And this, if you're worried about this, you can put parentheses around it. That's fine. To make sure that that squared is just part of that, and it should be fine. Now I have my net force. I can update my momentum. P plus F net times dt. I can update my position. R equals R plus P over times dt over m. Not v, right? Because I just updated the v. Don't use that v. I need to do P over m. Now I'm going to update time. Now I'm going to end it. So print R. I don't really, that's fine. Let's just print R equals R. And let's just run it and see if things are working. Because it could make a mistake. Once upon a time, I made a mistake. So this says after 1 second, it's still off the ground, right? It's still 8 meters high, but it's 13 meters down. So I want to know where it is when it gets back to the ground. So let's do this. While r dot y is greater than or equal to 0. So then it'll keep running. It starts at 0. It'll keep running until it gets back to 0 or lower. And you see here, it did go below there. That's fine. It went 34 meters, 34 yards. That's a pretty good throw. Okay. But let's make a graph, because you know I'm going to make a graph. Graph equals G1 equals graph. Let's call this title football, American football. Y title. Let's plot the trajectory. So Y title is going to be equal to Y in meters. And then the X title is going to be equal to X in meters. And then I want to put the width at 400, height at 200. And then I need to make a graph. So F1 equals G curve, color equals color dot blue. Now I can graph that down here. So let's just put it right here. F1 dot plot r dot x, r dot y. R dot x is the x value, r dot y is the y value. And let's plot this. I still haven't saved it, so it's kind of bad. Football throw with air. Run it. There we go. Okay. So what we're trying to do, right? What are we trying to do? We're trying to find, now that looks very parabolic, but it's not quite a parabola. In fact, let me just go up here and increase this drag coefficient to 0.5 and see what happens. Okay, so you have more air resistance. And you can see that it's skewed a little bit, right? So it takes longer to go up than it does to get down because it's going slower. And I'm going to keep this one. Let's find the range for this value of drag coefficient because I don't really care. So that's a 45-degree angle, and it went 27.7 meters. Let's see if I decrease it to 40, what happens. So if I change this to 40, and I run it, 27.7, okay, it doesn't change too much. 27.64, let's see, 40, let's do it to 50. 20, so that's definitely shorter, okay. Let's go back to 45. I can't remember what that was. 27.72, not 27, so 20.72, and I have terrible memory. 40 is 27.76. So we could just play around with the values here for the initial angle and find out which one gives the longest. But I'm not going to do that. I'm going to do something more fun. So what if I do that for a whole bunch of different values of angles? And I plot the final x position. And then by looking at the data, I can find out which angle gives me the maximum range. That's what I'm going to do. So you could do this in a nested loop, but I'm going to make a function. And I'm going to make a bad function. But if you like Python, if you don't like Python, like programming is the worst thing ever I've seen in my life, then just say, okay, I saw the first part and I'm pretty happy. And I don't want to see anything else. It's too scary. I get that. But I'm going to make a function. So I'm going to make a function, and I want to pass to the function the angle theta. Everything else I'm going to leave as global, and that's a bad idea, but I'm going to do it anyway. So let's say this function, I'm going to call it x range. It's the range it goes. I need to say def x range, and I'm going to give it the angle theta. So I don't want to put theta right there. Okay. Let's call this actually theta t for temporary theta. And now in this function, I'm going to do the following. I'm going to have my r vector. I'm going to put that down here. This I'm going to put down here. I want to include those because I need to reset those. Okay. V0 I'm going to include in there. I need to put in there, and this I need to put in there. And I need to tab and dent, because I need to reset the time, I need to reset the position, I need to reset the initial momentum, I need to calculate the momentum, and this is going to be theta t, because that's what the variable I'm passing to the function. And then all this stuff I'm going to do, so I'm going to tab that in. I'm not going to plot it. So once it gets done to r equals 0, I don't want to print r, I want to return, I'm going to return r.x. I'm going to return the x value of that. Okay, let's see how this works. All I've done is made it a function. So let's say print x range 45 times pi divided by 180. So I already know what the answer should be. I know what the x value should be. It's going to run that same calculation with that angle, and it's going to return the x value. And that's what I had before. So it looks like it's working. So now what I can do is say theta equals 10 times pi divided by 180. So 10 degrees. D theta equals 1 times pi divided by 180. So I'm going to use theta, calculate the range, increase my value of theta, calculate the range, increase my value of theta. And so I'm going to graph it. So that means that this y title is going to be actually range, and the x title is going to be theta in degrees. Let's do degrees. Let's do it. Okay, so now I'm going to say while theta is less than, how high of an angle do I want to go to? Let's say 60 degrees. While theta is less than 60 times pi divided by 180, do the following. Calculate the range. So I'm going to say x temp equals x range theta. So now I have it as a variable. I like to do it that way. Now I'm going to plot that. So f1.plot, I want to plot theta on the horizontal versus the range. So it's going to be theta x temp. Now I'm going to increase the value of theta. Theta equals theta plus d theta. And then just keep doing it until it gets to 60 degrees. And it plots the range so we can see how that changes. Let's see if this works. If it does, I'm going to be very surprised because I make mistakes all the time. And oh my gosh, it did work. So as I increase the angle, I plotted it in radians. So let's plot this theta times 180 over pi to convert back to degrees. I think in degrees. I don't know why. Okay, so you can see it's a little jagged, and that's fine. So up here at 40.7 degrees, I have a maximum range. And as I increase my angle, the range decreases. As I decrease the angle, the range decreases. So it did indeed work. Now, we can test this thing to see if it actually is working. And to do the following. What if I turn off air resistance? If I turn off air resistance, then I know what the answer should be. It should be 45. So I can do that by putting a 0 drag coefficient. If I run that, then I get a max right there. It's right there at 45. Right there, see? Beautiful. Okay, I don't want to turn that off. You can change the drag coefficient and see what happens. But see, I can do whatever I want now. I can change the initial position, the y value. I can change the y value. I don't have to start from the ground. So let's start 3 meters up, okay, just for fun. So I'm going to put this at y equals 4. I change it to 4. And I'm going to see what the final position is. Now you'll notice that the range is even at a lower angle. And so that kind of makes sense. Both of these make sense. If you shoot it at a lower angle, then you have less time to slow down. That drag coefficient is going to slow down the ball the whole time. So you don't want to waste all your time going up higher. You want to go down lower. So you can have more forward velocity while you have the time to have speed. So, okay. Let's put this back. I'm going to keep it like that. I'm going to save it. So if you haven't seen functions in Python, that wasn't the best example, but it's very useful. It's a very cool way to think about things. And a lot of times, that's the only way you can calculate this stuff is to change the value and see what happens. It's like a brute force thing, but making the computer be the brute. And I'm okay with that. That's it.